Okay, hi everyone. Okay, so I'm sorry, but I can't make class today. It's like I know it's supposed to be in an hour, but something came up, so I have to go like pretty soon. So I'm going to just like make a video, go over all of the stuff and explain all the questions and information we're gonna have for our last class. So today's class is going to be on functions, and so let's just get started. Okay. Wait, how do I okay. Am I able to mark up? Okay, okay, I can do this. Okay. So sorry, I'm not gonna use my iPad, so this is just on my computer. So pardon if I have like if it's very messy. All right. So functions. Functions are mathematical machines with only like one output for every unique input. So you can input like any numbers into them, right? And then they're gonna give like you have a functional equation, but you plug the number into the functional equation and whatever number you get out is going to be the output. So functions are commonly represented, I'm sure you guys know this, so like as f of x. When we plot them by graphing x, we usually plot them by graphing x on like a horizontal axis and then y or the output on the vertical axis. So if we want to graph the function f of x is equal to 1 over 1 plus x squared, we kind of just take in like, is this recording? Okay. We can kind of just take in, what is it? Just test a few points, right? So if x is 0, for example, we're gonna have 1. So it's kind of like it's gonna be here. And then as x gets greater, the function decreases, right? Because the denominator is increasing. And so as we take negative values of x, the function also decreases. So, but however, because there's an x squared, the denominator is always going to be positive because x squared is positive. So we're going to have some function that kind of looks like this, right? Okay, I'm just gonna like continuously save these. Okay, so inputs and outputs. Sometimes we cannot just like plug anything into a function. We need to like make some rules, right? Sometimes, and so we define the set of allowable inputs to a function as its domain, and usually you can assume that the domain consists or is only restricted to the real numbers. So it doesn't necessarily have to be all the real numbers, but it can only be real numbers. And likewise, the set of all possible outputs of a function is called its range, right? And that's also usually restricted to real numbers. So if we're trying to do this, find the domain and range of the function f of x equals x over x plus 1. We can see that we can kind of plug in any x in here except for -1. Because if we plug in x equals -1, that makes the denominator 0, right? So f of -1. Sorry, this is really bad Marco tool, but it's going to be -1 over like 0, right? And that's not allowed. So the domain would be like all the reals except like -1. I kind of forget how you mark it, but like yeah, all the reals except for -1. And then the range, if we can see here, we can kind of get like all real numbers from the range, right? But except for 1. So if we all right, so I'm gonna change to text. So, wait. So for example, if we wanted, so we said y equals x over x plus 1, we kind of manipulate to get in terms of x, right? So like, or we get x in terms of y. So then we can kind of see what we can plug in x to be. So we get move x plus 1 to the other side, we get x is equal to xy plus y. And then move x to the other side, so we get x times 1 minus y is equal to y. And then we get the x is equal to y over 1 minus y. So in this case, it's pretty clear now that we cannot have y is equal to 1. So the range is going to be all real numbers except for 1. So I'm just going to type it out. So range is all reals except for 1. This is much easier than like drawing it out. Okay. Function compositions. So you might think like, okay, we can take inputs and outputs, but what if we input an x into a function and then we take the output and we put it in the function again? Well, that's just a lot of function compositions. So we usually write like if we do that action n times, we write f to the power of n, so f like to n exponent, and then we write x. So notice that this is not equal to the value of f of x raised to the nth power. This is just a completely different notation. We can also take f of x and put it into a completely different function, right? Like say g, and then we will denote that as, I kind of couldn't write it on the keyboard, but it's supposed to be like g and then a little circle f, right? Okay. Just a comprehension question. Why do we need to make sure that f of x is in the domain of g? Well, because we're kind of taking f of x and then plugging it into g, right? And domain of g is defined as all the allowable inputs into g. So that's intuitively that makes sense, right? F of x needs to be in the domain of g. All right, so find a counterexample to the statement like f of g of x is equal to g of f of x. Well, this is like very simple, right? So if we have like x is equal to, oh my god, that's so scary. Okay, can't really, can't control z. Okay, let me just write it. So you have f of x is equal to like square root of x, for example, and g of x is equal to x plus 1, then f star g is going to be equal to square root of x plus 1, right? But however, g star f is going to be equal to square root of x plus 1. And those two things are definitely not equal. Square root of x plus 1 does not equal square root of x plus 1. Okay. Even and odd functions. So when a function f satisfies that for all x, f of x is equal to f of negative x. So we plug in x, we take the output, and that is also equal to, if we plug in negative x and take the output, then the function is defined as even. When f satisfies f of x is equal to negative of f of negative x, then f of x is odd. So the graphs kind of look like, so for even, if all, say like, if we take all positive x and plug it in, and it's whatever function it looks, I don't know, something, actually no, that is not a function. Just say that it looks like this, right? Then if we take all the negative of the domain, so all the negative numbers, then they're going to be equal. So we're going to have this kind of symmetry then, right? So that means for all even graphs, even function graphs, the graphs are going to be symmetrical with respect to the y-axis. So for odd, it's almost the same, except that if we take all the positive inputs and we graph it, say just that some arbitrary function looks like that, then f of negative x, it's going to be like the same magnitude, but kind of flipped across the x-axis because we have a negative sign in front, right? So it's going to look something like this. So by definition then, this is kind of a reflection about the origin instead of about the y-axis. So graphs with all odd functions are symmetrical about the origin. So okay, example, when is the function in the form of a polynomial odd? All right, so kind of polynomial functions, if you guys aren't familiar, it's like a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 and so on, right? Plus a sub 0. So when is this let's say 1 is this odd, right? So we need this function, arbitrary function, to satisfy f of x is equal to negative of f of negative x. And so if we plug in negative x, we want like this thing to be the negative of that. So the only way that can happen is if all the exponents that x is being raised to are odd, right? Because if we have some, say like coefficient a times just any x to some power, so this is to some power, we need this to be equal to negative a times negative x to that same power, right? So for this to be true, we must have this negative somehow be able to bring it out and then cancel with this negative in front. This means that n must be odd. So it's a polynomial function is odd when all of the exponents, so in all of the terms, are odd. And as you might guess, for a polynomial function to be even, then all of the exponents and all of the terms must be even. Because then, yeah, because for even, this negative sign does not exist, right? So that means this negative sign should be multiplied an even number of times to be 1 at the end, right? So we're gonna go through some special functions. So first special function is the absolute value function. So if you guys aren't aware, then the absolute value function f of x is equal to absolute value of x looks like this. This just means that whenever we have a negative value in the output, we take the negative of that, which gives us a positive value. So what is f's domain and range? So for if f of x is equal to absolute value of x, then f's domain can be all real numbers, right? Because that, as you can see, this kind of goes on forever. Like there's no restriction to x values. However, the range is always greater than or equal to 0. Because by definition, we are taking the magnitude of everything. So if it's negative, then we must turn to a positive number. So the range is that. All right, solve this equation. So to solve absolute value equations like this, it's easiest to just take two cases. So the first case would be case 1, when x plus 2 over 3x minus 1 is equal to 5. And then case 2 would be when x plus 2 over 3x minus 1 is equal to negative 5. And then we solve these simultaneously. We always check for extraneous solutions. Okay, so I'm just gonna do the first case. So case 1, we move everything to so we get x plus 2 is equal to 15x minus 5. And then, sorry, so that gives us 14x is equal to 7, right? So x is equal to 1/2. And then we can just do the same for the case 2. Or here, I'll just write it. I'll do it. So case 2, x plus 2 is equal to negative 15x plus 5. So that means that 16x is equal to 3, so x is equal to 3 over 16. All right. So those are the two solutions. Next special function, we have the floor function. So it's hard to format it, so I'm just going to write it. So floor function would be, if we define it as f of x, it's going to be when f of x is equal to, it's like this symbol. So it's basically just finding, it takes an input x and it outputs the greatest integer that is less than or equal to x. The greatest integer that is less than or equal to x. And the fractional part is going to be equal to just x minus the floor of x. And the symbol's like that because it kind of looks like the floor, right? It's like bracketing the floor. And the ceiling function is very intuitive. It's just denoted as this. And it's going to be the least integer that is, wait, sorry. So before, if I misspoke, the floor function is the greatest integer that is less than or equal to x, and the ceiling function is the least integer that is greater than or equal to x. So it looks like this. Right, and then so let's example question, are the absolute value and floor ceiling functions odd, even, or neither? So if you take a look back at the absolute value functions, it definitely looks even, right? Because it's symmetric about the y-axis. So absolute value is even. However, the floor ceiling functions are neither because, all right, so let me just graph the floor function. So it kind of looks like, so we take 0. For all integers, the floor function is going to be equal to itself, right? Because the greatest integer that is less than or equal to an integer is itself. So as all of the integers, we have them equal to themselves. However, there's kind of like there's going to be an open circle because then this is like closed and then here and then it's like another open circle. So it just continues. Right? And then same thing for here. So open circle means that like at that specific x value, that is not a y value, even though before it's kind of gives the trend like that, it just jumps up every time. So it's very clear that, right, like this is not symmetrical about neither, this is symmetric about neither the y-axis or nor the origin, so it is not even or odd. And same goes for the ceiling function. It looks very similar to this. It's just kind of this just shifted up a little bit, up by 1. All right. Okay, next special function. So functions with multiple cases. What I mean by this is like if we have a function f of x, yeah, again, I am so sorry about this looks so bad. Okay. F of x is equal to, and then it's kind of like a bracket. And then it has some like function g of x and then some function p of x, or it has multiple. It can have like as many as you want. But like say that this is like x squared minus 1. So this is just an example for, let's say, like x, all x less than 0. Right? And then say this is like what? Like x minus 1 for all x greater than or equal to 0.哦，准备啦！哦，我在录 video。And then so this is like it looks like this. So like this is an example. So it's going to be like at the cutoff point, it kind of looks different. So this is like it kind of looks like this, and then but it goes like this, right? Because this right side, the greater than 0 side, it's kind of the function x minus 1, and then the less than 0 side, it's the function x squared minus 1. Right, so just one thing to touch upon, heavy side step function, that's just that's kind of similar to, well actually no, it's not. So the heavy side function is defined as 0 for x less than or equal to 0 and 1 for x greater than 0. So you might think like, oh, what's the use of defining this function? So what does it look like? It kind of just looks like it's all like a straight line here, right? And then as a circle here, and then just it's just 1 for like all the positive integers or positive numbers. Well, that has its uses because you can kind of manipulate multiple heaviside functions, like add them together to get very like what is it called? Like different functions with different heights and also like the turning points at different places. me just like point an arrow to this. Okay. So transforming functions. So I'm just going to go over this super quick. Transforming, if we have f of x and we take the transformation f of x plus a, we take x plus a within x, then this is equal to f of x shifted a to the left. If we add some constant a to f of x, then this is just f of x shifted a units up. If we multiply it by some constant x, this is a vertical stretch. So if a is greater than 1, then it's going to be like stretched. If a is less than 1, then it's going to be kind of squished. It's like, and then kind of the opposite, if ax is with inside the argument. So if a is greater than 1, these are all like ones. It's like a is greater than 1, then this kind of becomes shrunk. And then if a is less than 1, it is like horizontally stretched. All right. So lastly, we have a couple of exercises. I'm going to like write them and then we see. All right. Let me just, I'm just gonna paste this. This like. Okay, so the first question, I'm just like pulling these on my up on my computer because all right, so the first question is let this bracket, let bracket of x, denote the greatest integer function. And let this fractional, this wavy bracket x equal what it usually equals. Right, so x minus bracket x. So this is greatest integer, so this is floor. Right, and then so if z is equal to the fractional part of root 3 squared minus 2 times the fractional part of square root of 2 squared, all over the fractional part of root 3 minus 2 times the fractional part of root 2. Then find the floor of z. All right. So this is the question. Feel free to pause the video and try to work through this question by yourself. And we're going to do it. I'm going to explain it soon. Let me just find a way to why. I'm not sure how I am supposed to. Okay, it's okay. So I'll just like wait. I'll just use this next slide. Right. Right. So because we know that root 3, the floor of root 3 is equal to 1, right? Because root 4 is 2 and root 1 is 1. So the floor of root 3 is going to be equal to 1. So we know that the fractional part of root 3 is going to be equal to, just going to type it. The fractional part of root 3 is going to be equal to square root of root 3 minus 1. And then we have that squared minus 2 times, same goes for root 2. It's going to be square root of 2 minus 1 all squared. And then we have this all over, just again plugging it in, square root of 3 minus 1 minus 2 times square root of 2 minus 1. Does that make sense? Because we know that root 3, that the floor of that is equal to 1. So we have the fractional part of root 3 is equal to root 3 minus 1. Because we know fractional part of x is equal to x minus the floor of x. And then we just like do the same thing for both sides. And we get this long expression. And then once we expand out this long expression, trust me, in the end, it will be simplified to like z will simplify to -2 minus 2 times root 3 plus 4 times root 2 all over 1 plus root 3 minus 2 times root 2. So if we further like simplify this, this is going to give us z equals -2. And clearly we have the floor of z is equal to -2. So that's our answer. All right, next question. Okay, this is also a long one. Okay, let f be the function from real numbers to real numbers defined by f of x. This is one of those like piecewise functions that we have. F of x is equal to x plus 2 if 3 is the divisor of the floor of x. So if 3 divides floor of x. Otherwise, we have f of x equal to x minus 1, otherwise. So 3 does not divide floor of x. All right, so as usual, like floor of x is the greatest integer function. So compute f of f of f of f of f of pi. So I am not going to write that out. I'm going to. So f of f, 1, 2, 3, 4, 5. 1, 2, 3. Yeah. So what is this? Again, feel free to pause this video and think about it for a bit. All right. So we have pi. So if we first we can just work from the inside out. Right. So this is like floor of pi. If we want to plug pi into f, so we get f of pi. So if 3, we want to check if 3 divides the floor of pi. So floor of pi is equal to 3, and 3 divides 3. So we're going to have this is equal to f of f of f of f of pi plus 2, right? And then this is equal to, so again, we just plug this in again. So, right, so floor of pi plus 2 is going to be equal to 5, and 3 does not divide 5, so this is going to equal f of f of pi plus 2 minus 1, which is pi plus 1. Right, and then we find that, okay, so and then f of pi plus 1, so floor of pi plus 1 is going to be equal to 4, 3 doesn't divide 4, so we're going to have that is equal to f of pi plus 1 minus 1, which is pi. And then we just do it again. So it's like we get f of pi plus 2, and this is going to be equal to pi plus 1. So our final answer is pi plus 1. So just to reiterate, we kind of just literally just work from the inside out, using the function definition to find the value of this function. Just make sure your work, you have to be careful because there's like so many f's, right? But it's quite easy to take the floor of pi plus any integer because the floor of two numbers add together, or like the floor of x plus an integer is equal to the floor of x by itself plus that integer. All right, so last exercise we're gonna do is 11. Okay, so this is find the coordinates of the points of intersection of the graphs of the equations y is equal to, so the value of 2x minus 2 and y is equal to negative absolute value of 2x plus 2. All right. So again, pause this video if you want some time to think about this. All right, so we're gonna solve this just by equating the y's equal to each other. So we have 2x, absolute value of 2x minus 2 is going to be equal to a negative absolute value of 2x plus 2. All right, so what do we get from this? So if x is greater than or equal to 0, then we get 2x minus 2 is equal to negative 2x plus 2. So this gives us x is equal to 1. So that's good because x equals 1 is greater than or equal to 0. Right, so if x is negative, if x is less than 0, then we have negative 2x minus 2 is equal to 2x plus 2. Right, and this gives us x is equal to negative 1. Right, so this is also consistent because x equals negative 1 is less than 0. So we have our two solutions, which are, so x is equal to 1 and x equals negative 1 are solutions. So the points of intersection of the graphs are just, if we plug in x equals 1, then we get y equals 0. And if we plug in x equals negative 1, then we also get y equals 0. So these are the 2 points. All right, so I think that concludes everything today for the last week of this class on functions. So this was very messy. I'm sorry about that, but I will again, I will post these slides to class 2. All right, so again, I'm sorry about not being able to make class tonight, but yeah. I will also post the final exam sometime probably tomorrow or tonight if I have time. All right. So bye everyone. Thank you for watching.